This video will cover the basics of Q learning. A state is what the agent can see. This could include the health of the agent, its position, or its velocity. An action is what the agent can do. This could include jumping, moving left, or moving right. A Q value is the expected reward for choosing an action at a certain state. Q learning agent takes many actions at different states while it trains, and it remembers the results of these state action pairs as Q values. A trained agent will choose the action with the highest Q value for its current state, since the highest Q value indicates the highest expected reward. A Q table is used to keep track of the Q values the agent has learned. In the example game on the right, we have 9 states, and the agent can choose to move up, down, left, or right. The movements up, down, left, right are actions that can be taken by the agent, while S1, S2, and so on are the states the agent could be in. If I wanted to know what the exact reward is for moving down at state 1, I could look here. The value is currently 0 since the agent hasn't been trained. If an agent moves anywhere except S9, it receives a -1 point penalty. Reaching S9 gives the agent a reward of 10 points, and the game ends. The agent can't go off the board, so moves that would put the agent off the board are marked as X's in the Q table. If the agent moves down from state 1, it will receive a penalty of -1. We can then find the difference between this reward and our current Q value, which is -1. After multiplying by a learning rate of 0.01, we get a new Q value of -0.01. The learning rate is used to keep updates small and ensures that the Q table isn't changed too much by a single update. If the agent moves right from S4, it gets a penalty of -1, and its new Q value is calculated in the same way. Here, the agent moved from S5 down to S8. The agent moved right from S8 to S9 and got its reward of 10 points. The reward is calculated in the same way, but now the result is positive 0.1 since the reward was 10 instead of -1. Since the agent found the reward, this training episode ends. This works to indicate where the agent should go from state 8, but not from any other state. We know that there is a benefit for the agent to move right from state 7, since it can move right again on the next move to get a reward of 10. The agent currently doesn't consider this benefit, so we are going to modify the way it updates. If the agent is at state 7 and moves to state 8, we will look at the maximum Q value for state 8, since the agent can take that move next. In this case, the best move from state 8 is right, with a Q value of 0.1. We could just add this value to the reward, but since the agent doesn't have its reward yet, it would make sense to discount this future Q value. First, we will find the difference between the reward plus discounted Q value and the current Q value for moving right from state 7. The reward for moving right from state 7 is -1. Add this to the Q value, 0.1, discounted by 0.5, and subtract the previous Q value of 0 for moving right from state 7. The result is -0.95. We take this value and multiply it by the learning rate of 0.01, and then add this value to the previous Q value. Moving right from state 7 now has a Q value of -0.0095. This value is slightly better than -0.01, which would have been the Q value without including the next best move. There are a couple ways we could choose the agent's moves while it trains. We could choose based on policy, but once the agent finds a reward, it will likely choose the action every time, even if another move was actually the best. For example, if there was a reward at S6 and a larger reward at S8, the agent might choose to move to S6 instead of S8 each time it gets to state 5. This means it would never get the best possible reward from state 5. We could also try to move randomly, but the agent wouldn't be taking advantage of the policy it already learned, which might make training slower and less effective. It's important to use what the agent has learned from training, while also giving it the opportunity to explore its environment. To get the best of both worlds, we can use the Epsilon-Greedy strategy. We keep an epsilon value, which is the probability the agent will choose a random move. Starting with an epsilon value of 1 means that the agent will choose a random action with a probability of 100%. We can also use the agent's Q table to select a move with probability 1 minus epsilon. As the agent learns, we will reduce or decay the epsilon value so that the agent chooses more moves using its policy and chooses less moves randomly over time. Epsilon can be decayed after each training episode is complete. The agent will reduce its epsilon by the epsilon decay every time this function is called until it reaches final epsilon. It is prevented from going lower than final epsilon by the max function. First, we make sure the current state is in the Q table. If not, it is added with 0 values. Then a random number is chosen between 0 and 1. If it's less than epsilon, a random number is chosen corresponding to an action. If the number is greater than epsilon, use the agent's learned policy to choose a move. In the function, this is the index of the max Q value for the state. Returning 0 will move the agent left, 1 will move the agent down, 2 will move the agent right, and 3 will move it up. The update function first makes sure the current and next state are in the Q table. If not, it adds them. Then the difference between expected and actual results is calculated, similar to what was done on slide 10. Then this value is multiplied by the learning rate and added to the old Q value to update it. Thanks for watching. I hope this video was helpful.